Hi, welcome to this test or study guide, however you choose to use it, on stoichiometry. This video, warning, it's going to be long because I'm going to work out every single one of these problems, but you should take a minute to do that first. So here's the first set of questions. We're looking for what is a mole and then the formula mass of these three compounds. So to answer the first question, what is a mole? A mole is a name for a number, and that number is 6.02 times 10 to the 23rd. We also call it Avogadro's number, and really all it is a group of atoms bundled together into this quantity so that we can actually work with them. We call that number a mole. Next is the formula or the molar mass of K3PO4, potassium phosphate. In order to do this, I would do what's called, or what I call, a QMT chart. And the QMT chart, you list all of the elements, and then you list their quantity, their mass, and the total. In K3PO4, I have three potassiums, 1 phosphorus, and 4 oxygens. The mass is pulled from the periodic table, which I have a little pocket periodic table that I like to use. The mass of potassium is 39.10. I'm just going out to the whole numbers here. Phosphorus is 31, and oxygen is 16. We multiply going across to find the mass of all of the potassiums. 3 and 39 is 117. This is obviously 31, and 4 times 16 is 64. Yes, it is. So we are going to add all of these going down to find out what the molar mass is, and that comes out to 212 grams per mole. I'm going to do the same for the calcium hydroxide with 1, 2, and 2. Don't forget those parentheses. Calcium is 40, giving us 40 in total. Oxygen is 16, giving us 32. Hydrogen has a mass of 1, giving us 2 in total, and this comes out to 74 grams per mole. Now, this is calcium chloride decahydrate, and all that really means is that this calcium chloride has some water molecules stuck to it, and the quantities is what's going to be weird here. That's all. We still have 1 calcium. Here we have 2 of the chlorines. This 10 is like a coefficient for the water, so 10 times 2 is going to give me 20 hydrogens, and 10 times the imaginary 1 gives me just 10 oxygens. Calcium again is 40, chlorine is 35.45, so it's 35. The hydrogen has a mass of 1, and oxygen is 16. Multiply across, that is 70, 20, and 160, and then we're going to add them all up going down the total column. And that comes out to 290 grams per mole. Okay, so the next question is to find the percent by mass of certain elements in those same compounds. I am a knucklehead and just erased all of my work, so I'm going to have to do it again. So if you have digital work and you just erased it, hit undo a bunch of times. We are looking for elements within the compounds you've already found the molar mass of. So once we have the molar mass, we're looking at the whole QMT chart. Remember, this came out to 212. This is the total. So this is what we're going to want to use on the bottom of our percent by mass. And what we're going to want to put on the top is the amount of all of the phosphoruses, which in this case turns out to just be 1 phosphorus. We would do 31 divided by the total, 212, and then we're going to multiply that by 100. 31 out of 212 times 100 gives us 14.6% phosphorus. The calcium hydroxide had a total of 74 grams per mole, but in this case, we are looking to only find the percent by mass of the oxygen in here. If you look back at your QMT chart, or you just multiply this 2 times the mass of oxygen, we would be working with 32 grams of oxygen in this total 74. So we can take this, it's a little less than half, 32 out of 74. Comes out to, remember we're going to multiply this also by 100 to turn it into a percent because it starts out as a decimal. We are getting 43.2% oxygen. Last up is the percent by mass of water in that calcium chloride hydrate that we were working with. One water has a mass of 18 grams, but here we have 10 of them, meaning that the water in total is going to be 180 grams. If you were to look at the QMT chart, you keep the H and the O separate down at the bottom. Remember, we had 20 of the hydrogens, each coming in at 1, giving us a total of 20. And then we had 10 of the oxygens, each coming in at 16, giving us 160 total. This tablet is making me crazy. That's where we get the 180. It's the 160 plus the 20. We're going to take that 180, divide it by the 290, and we are going to, of course, multiply that by 100. This comes out to 62.1%. The next thing we want to do is find the percent of hydration for each of these, which really just means the percent by mass of water. And we also want to name these compounds. This compound would be called barium chloride dihydrate. Again, we're just going to name the ionic part, and then we put a covalent prefix on this 2 here, and then we just name it hydrate. Now, to figure out the percent by mass, again, we're going to do a QMT chart. I know you love them. We are going to list out all of the elements. We're going to count them all up. Pull their masses from the periodic table. Multiply going across. Add going down to figure out the molar mass. And we're going to add just the hydrogen and the oxygen to figure out the total mass of the water. Then we'll take that 36 divided by the 243, multiply by 100, and find the percent of hydration. This came out to 14.8% water. This compound is called cobalt 2 chloride hexahydrate. Just because it is a hydrate does not mean that we can ignore the fact that we sometimes need Roman numerals. For the cobalt, we need this Roman numeral because it is a transition metal. Okay, in this compound, we have 1 cobalt, 2 chlorines, 12 hydrogens, and just 6 oxygens. We have a mass on the cobalt of 59. Chlorine is 35, hydrogen is 1, and oxygen is 16. Multiply across 59, 70, 12, and 96. If we were to add all of those together, you get 237 grams per mole. Then we can take just the total of the water, which is going to be this 12 plus the 96. That comes out to 108, meaning I have 108 grams of water per every 237 grams of this hydrate. So what I'm going to do is divide those two values, 108 out of the 237. And of course, I want to multiply this by 100 to turn it into a percent, and I am going to get 45.5%. I apologize that I am now disappeared on the math bubbles. No reason other than tech problems. My last drawing program was giving me a hard time. So here we are going to convert between grams and moles. It's important to note, just for your own sanity, that I have chosen the same compound for both sides of this. So You'll have to do a QMT for NaCl and KMNO4, but you don't have to do them again when you get to this side. Just something to note. We are going to begin with the QMT for sodium chloride. I have sodium and chlorine. One of each. Sodium's mass is 23. Yes, it is. Chlorine is 35. That gives us 23 and 35, which is a total of 58 grams per mole. Now I'm going to do the moles to grams and then the grams to moles, and then I'll move on to the next substance. So to begin, we had 2.58 moles is equal to, I don't know how many grams, so I'm going to label it X. I do know from my molar mass down here that 1 mole has a mass of 58 grams. So here I'm just going to cross multiply. I'm going to get 1x, so really just x, and 58 times 2.58 is 149.64 grams. Then I am going to do the other side, which was 3.98 grams is equal to, I don't know how many moles, but what I do know is that 58 grams is equal to 1 mole. So I'm going to cross multiply. I'm going to move my work over here in this left corner. I get 58x is equal to 3.98. Divide both sides by that 58 to get the x by itself. And then x is going to be a very small number. 3.98 divided by 58 is equal to 0.069 moles. Next up, we are going to do the QMT for the potassium permanganate. I have 1 potassium, 1 manganese, and 4 oxygens. Potassium's mass is 39. The manganese is 55. And oxygen, of course, is 16. And that is 64. We're going to add them all going down, coming out to 158 grams per mole. I'm going to begin with the moles. 0.36 moles is equal to, I don't know how many grams, but I do know that 1 mole is equal to 158 grams. And I got that from the QMT chart. So here I'm going to cross multiply again on the x. I'm getting just 1, so it's x. 158 times 0.36. That comes out to 56.88 grams. Moving on, I have 23.6 grams is equal to, I don't know how many moles, but I do know that when I have 158 grams, I have 1 mole. So I'm going to cross multiply. I get 158x is equal to 23.6 times 1 is just 23.6. I'm going to divide both sides by that 158 to get the x by itself. I wind up with 0.149 moles. Last up is the magnesium nitrate. I have 1, 2, and 6. Magnesium is 24. Nitrogen is 14, and oxygen, of course, is 16. Take those totals across. Is that 96? Yes, it is. Going down, I get the total. Right now, I would like to have 1.14 moles. that is equal to, I'm not sure how many grams, but I do know that 1 mole would be equal to 148 grams. So I'm just going to cross multiply, and I am going to get very simply 1.14 times the 148, and that comes out to 168.72 grams. Last up is if I had 84.2 grams, how many moles would that be if I know that 148 grams is equal to 1 mole? Here I'm going to get 148x is equal to 84.2. Divide both sides by 148 to get x by itself. And x turns out to be 0.569 moles. Moving right along, we have a mole ratio question, actually 2 mole ratio questions, and they are based on the synthesis of ammonia from its elements. How many moles of hydrogen are required to form 0.27 moles of ammonia, and how many moles of ammonia can be formed from 24.8 moles of hydrogen? First off, we have to start with a balanced equation. So we are making ammonia from its elements. Ammonia is the common name for NH3, and the elements that make that would be nitrogen, which is diatomic, and hydrogen, which is diatomic, and we'll have to balance this. I can do that by putting a 2 out in front of the ammonia. That gives me 6 hydrogens. 6 hydrogens would require a 3 out in front here, and the nitrogen is 2 on both sides. So those are our coefficients that we will be working with. The first question was, how many moles of nitrogen are required to form 0.27 moles of the ammonia? So I'm going to take my 3 moles of hydrogen and say that that is equivalent to forming 2 moles of the ammonia. But the question is, how many moles of the hydrogen can I make if I'm only going to use 2, or I'm only going to form rather 0.27 moles of the ammonia? So I'm just going to cross multiply and solve for the x. This gives me 2x, and 3 times 0.27 comes out to 0.81. I should have known that one. Divide both of these by 2 to get x by itself, and that comes out to 0.405 moles of the H2. Now, this very commonly could turn into it asks you about grams perhaps. For that, you would just do a gram and mole conversion. The next question was, how many moles of ammonia can be formed from 24.8 moles of hydrogen? And again, we're going to set up a ratio. For every 3 moles of hydrogen I use, I can make 2 moles of ammonia. If I want to use up 24.8 moles of this hydrogen, how many moles of ammonia can I make? So again, I'm just going to cross multiply and solve for x. In this case, I would get 49.6 is equal to 3x. Divide by 3 on both sides to get x by itself. And x turns out to be 16.5 moles of the NH3. The next question set is on stoichiometry. It says to consider the formation of iron 3 chloride from its elements, how many grams of product can be formed from 38.7 grams of iron with chlorine in excess, and how many grams of chlorine are needed to form 59.7 grams of product? This one's going to be fun. First off, we have to start with a balanced chemical equation. So we are forming iron 3 chloride from its elements. Iron 3 chloride would have a charge of a formula of FeCl3. The chlorine has a -1, which crisscrosses here. Iron 3 tells you you have a 3. This is going to be formed from its elements, which are iron and chlorine, and it's important to remember that chlorine is diatomic. So in order to balance this, if I put a 2 out in front of the iron 3 chloride and a 3 in front of the chlorine, I'd have 6 chlorines on each side. If I put a 2 right here, I have 2 irons on each side. The question was how many grams of product, so this is X grams, can be formed from 38.7 grams of iron. 38.7 grams of iron. And chlorine in excess means you have essentially an unlimited amount of chlorine and it's not going to hamper or tamper. Tamper? It's not going to slow down your reaction at all. So now that I have my balanced chemical equation, I have to take this number and I have to convert that into into moles. 1 mole of iron is 56 grams, and I could have done a QMT chart if this were a compound, but it is just an element, so I could just pull that information from the periodic table. I'm trying to figure out the number of moles, so that is X. In this case, I would get 56X is equal to 38.7. Divide both sides by the 56 in order to get the X by itself, and I would have 0.69 moles. Next, I'm going to do a mole ratio comparing the amount of iron to the amount of iron 3 chloride. The cool thing here is that these are working in a 2-to-2, meaning that whatever number of moles of the iron I'm working with, that's the same number of moles I'm going to get for the iron 3 chloride. No problems there. It's a 1-to-1. I love when that happens because it's really like skipping this step. We don't have to set up a ratio. And then finally, I have to turn this number of moles of iron 3 chloride into grams because that is what the question was asking right here. So here I'm going to take that 0.69 moles and I'm going to convert that to, I don't know how many grams. We're trying to figure that out. I know that 1 mole of this iron 3 chloride is going to be equal to whatever the QMT comes out to. So I'm going to come up here to the corner and I'm going to do a real quick QMT on the iron 3 chloride. I have 1 and 3, 56 and 35. That gives me 56 and 105, which is going to give me 161 grams per mole. So that is the number of grams in 1 mole of iron 3 chloride. Crisscross to multiply. 1x is just x. I'm going to take that 161 and multiply it by 0.69, giving me 111.09 grams. All right, the next question asks, how many grams of chlorine are needed to form 59.7 grams of product? So this one's going to be a little bit tougher, and the reason is because they work in a 3-to-2 ratio. They are not a 2-to-2, or in other words, a 1-to-1 like it was before. This just means we actually have to work out the mole ratio, but that won't be a problem for us because we got this. So the first thing we're going to do, of course, is convert our unknown into, or rather our known value into moles. So I've already done the QMT from the last problem. I didn't erase that. We're going to keep that. So I know that 1 mole of this FeCl3 is equal to 161 grams. The question is, how many moles is it when I have only 59.7 grams? So I'm going to cross multiply. I get 161x is equal to 59.7. Divide both sides by the 161. And x is going to come out at 0.37, and that is the number of moles I'm working with. Now I need to do a mole ratio between what I have and what I want. I know that every time I do this reaction, I'm going to need 3 moles of that chlorine in order to make only 2 moles of that iron 3 chloride. But what if I only was going to make 0.37 moles of that iron 3 chloride? Then how many moles of chlorine would be required? Here I'm getting 2x is equal to the product of 3 and 0.37, which is 1.11. I'm going to divide both sides by 2 in order to get x by itself, meaning that x is 0.555 moles of chlorine. Finally, I'm going to take those moles of chlorine and convert them into grams because that's what the question is asking for. I know that 1 mole of chlorine has a mass of 70 grams. Now, it's 70 and not 35 because we're working with diatomic chlorine. So if you were to do a QMT chart, your quantity for the chlorine would be 2. 1 mole is equal to 70 grams, but how many grams is it if I'm working with 0.555 moles? 1x is just x, and that will be equal to the product of 0.555 times 70, and that comes out to 38.85 grams. Thank you for sticking with me through this very long test or study guide, however you choose to use this. We are down finally to the last topic, which is empirical and molecular formulas. All right, the mass of a substance is 150 grams per mole. The empirical formula is CH2O. What is the molecular formula? And a substance is 52.14% carbon, 13.13% hydrogen, and 34.73% oxygen. What is the molecular formula if its mass is 46.07 grams? Let's go. Okay, I know that I have a molecular mass of 150 grams per mole, and I know that my empirical formula is CH2O. So what I want to do is take that CH2O and find out its molar mass, or do a QMT for it. And the reason is because once I get that mass, I can divide with this number and figure out what that multiple was that was used to get up to the 150. So I have 1, 2, and 1. Mass of a carbon is 12, hydrogen is 1, and oxygen is 16. So we have 12, 2, and 16, which is 30. 30 grams per mole. So this CH2O comes in units really of 30. So we're going to take that 150 and divide it by the 30. 15 divided by 3 is 5. So that means my molecular multiple is 5. I am going to take every single subscript and divide it by, multiply it by this 5 in order to get the full formula. So that is going to give me C5H10O5. And if we were to take a QMT of this, we would get the 150. This is the set of information that we got from the second question. And we are going to assume that we are working with 100 grams of whatever the substance is. And the reason we do that is because we can very easily just convert all of these percentages into grams. Then what we're going to do with those grams is convert them into moles. So for the sake of writing and assuming that you already know what you're doing here, I'm going to kind of do 2 and 1. So 52.14 grams of carbon is equal to, I don't know how many moles, but I do know that 12 grams of carbon is equal to 1 mole. So this is going to give me 12x and 52.14. Divide both sides by 12 to get x by itself. And this tells me that I am working with 4.345 moles of carbon. Hydrogen is effectively the same. We have 13.13 grams of hydrogen, and that's equal to, I don't know how many moles, but I do know that 1.008 grams of hydrogen is equal to 1 mole. I'm going to do the same over here for the oxygen. 34.73 grams of oxygen is equal to, I don't know how many moles, but I do know that 32 grams is equal, I'm sorry, not 32. It's just 16. This isn't a compound. So this oxygen is not diatomic. It's bound to carbon and hydrogen in some combination. So that is equal to 1 mole. 16x is 34.73 grams. Divide both sides by 16. This gives us 2.17 moles of oxygen. I'm going to record all of this information over here underneath, and then I'm going to erase to give us some more room. Now I'm going to take each of these number of moles and I'm going to divide them by 2.17 because that's going to give us just 1 unit of oxygen, which is kind of related to our empirical formula because we want to kind of reduce all of our subscripts. So I'm going to take that number for the carbon. I'm going to divide that by the 217. 1303 divided by the 217. And then even though we know the answer to this, we should still put it on paper to show our work. So this is going to give us 1 oxygen very easily. We're going to calculate the others. This comes out to 2.002, which really just means 2 carbons. And then this 13.03 divided by 2.17 is giving us 6.004 hydrogen. So we're just going to take the 6. And this is the chemical formula that we're working with as of right now. C2H6O. And we need to do a QMT for this formula to then divide with this molecular mass over here to figure out if this needs to be multiplied at all. Because this is our empirical formula, it is the most basic ratio, and no subscripts can be reduced because we have just 1 of those oxygens. So doing the QMT here, I have carbon, hydrogen, and oxygen. Two carbons at 12 gives me 24 in total. 6 hydrogens at 1 apiece gives me 6 in total, and 1 oxygen at 16 gives me 16 in total. And let's find out. That comes out to 46. And considering that this is 0.008, and this really should have been 6.048, this is going to come out to 46.048. I am pretty satisfied with this answer. This right here matches this answer, meaning that we did not have a molecular multiple. The empirical formula and the molecular formula were the same for this compound. Thanks so much for being here. I know that this was a really long video. If you were able to do this well, I would say that you are a stoichiometry pro. If anything was troubling to you, I suggest you go back and check out the individual videos using the topic titles. some of the stuff gets pretty hairy and it all builds on itself. So it's important that you are able to identify what step to do and then how to do it. Just looking at the number of QMT charts that we did in this video, I very much recommend that you at least know how to do that, because at minimum you can get some partial credit just doing some of those QMT charts. Please subscribe so you don't miss our next unit. It's going to be a lot of fun. You can leave any questions you have in the comment section below the video. I will certainly come back to answer them. That's all. See you in the next one. Bye.